Hi, welcome to 7.3, proving that a quadrilateral is a parallelogram. Now we are on page 205, so make sure that you grab a half sheet of paper and glue it right on this. So basically the half of a quarter sheet. Okay, so make sure you glue it on. Okay, and do the same thing on page 206. So on page 206, please make sure you do exactly the same thing. We are going to use these diagrams to do two separate proofs, which are not going to be too hard. All right, now here's where the examples are going to go. So on page 207, you're going to put problem number 1 there, problem number 2 here, problem number 3 there, and problem number 4 right there. And there is no problem 5. So while we're in this page, let's go ahead and go over some of these theorems. Now, these theorems are going to seem very similar to the ones we did in the last lesson. And that is because now we're going to do the converse of them. In lesson 7.2, we started with if a quadrilateral is a parallelogram, then the opposite sides were congruent and the opposite angles were congruent. Here we're going to work our way backwards. So if in a quadrilateral, if the opposite sides are congruent, then it's going to be a parallelogram. So remember that a parallelogram is a quadrilateral where the opposite sides are parallel. So our goal is going to be to show that those sides that are opposite that are going to be parallel. So this is going to bring us back to chapter 3, where we learned about the converse of the alternate interior angle theorem, the converse of the, well, that's mainly the one that you're going to need. Those are the ones that are going to show you that a set of lines are going to be parallel. Okay, so we're probably going to go back and review a little bit more of those theorems later on, but make sure you guys know what I'm talking about. Okay, so here is the first theorem. The parallelogram opposite side converse, because we did the one with the theorem yesterday. Not yesterday, but in the previous lesson. So it says this: if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So here, if these two sides are congruent and these two sides are congruent, then we're going to do a proof on this one that it's going to be a parallelogram. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is also a parallelogram. Okay, so then this one is not a converse theorem, but it's a new one. If you have a polygon, okay, or if one pair of opposite sides of a quadrilateral are both congruent and parallel, then the quadrilateral is a parallelogram. Now, how do we know that? Well, think about this. If you were to draw a diagonal such as this one, okay, because those two lines here are parallel, this one is congruent to this one by alternate interior. This side is congruent to itself, okay? So by side angle side, these two triangles are going to be congruent, making this side right here congruent to this side right there. And now since you have a quadrilateral where the two opposite sides are congruent, that will mean that it's going to be a parallelogram based on this theorem right there. So it's a plan that I just gave you. It's not really a formal proof. Now on the next page, on page 208, you have the last theorem. Okay, the last theorem says this: if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Could you have written all these theorems as a biconditional? Absolutely. Those are the ones that say if and only if. But then again, that would be a little bit more confusing. So what are we going to do in the exploration? We are going to be proving this one right here and this one right here. Okay, So in order to do that, please go to page 205. And let's start with that one. Okay. Set up your two columns. So what do we have? Okay. What exactly is my given? My given is that I have those opposite sides congruent. So given, okay, what is given to me? The opposite sides congruent. You have BC congruent to DA and AB congruent to CD. That's what's given. Okay, so remember, my goal is to prove that this is a parallelogram. So in order to prove that this is a parallelogram, I have to prove to you that the opposite sides are going to be parallel. And that's how I can show you that it's a parallelogram. So I have to prove that AB is parallel to CD and that BC is parallel to DA. I have to show you that. Okay, so how are we going to do this? Okay, very, very simple. First off, we're going to need a diagonal. Okay, so from A to C, that's my diagonal. All right, notice that you have this congruent to this and this congruent to this. Those were given to you. This side is congruent to itself by the reflexive property of congruence. That means that these two triangles are congruent by side, side, side. Therefore, you're going to have a lot of angles congruent. So let's just go ahead and name these. Okay, so let's call this one here angle 1, angle 2, angle 3, and angle 4. Based on the fact that these are congruent by side, 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 angle 1 is going to be congruent to angle 3, and angle 2 is going to be congruent to angle 4. With that being said, because angle 1 and 3 are congruent by the converse of the alternate interior angle theorem, AB is going to be parallel to CD. Because 2 and 4 are congruent by the converse of the alternate interior angle theorem, BC is going to be parallel to DA. Okay? And since now I have shown that they're parallel, it's going to be by definition a parallelogram. So let's begin. First things first, list what is given. BC congruent to DA. And if I'm going too fast, pause it, go back. Maybe I can put it so that it plays a little slower. Give you guys a little more time. I don't know. All right. These were given. Second thing, I needed that diagonal AC. So AC is a diagonal. All right, and that is actually an auxiliary line. All right, it's an auxiliary line. Now, because it is a segment that has a common shared side with both triangles, AC is going to be congruent to CA by the reflexive property of congruence. So look, you have 3 pairs of sides. So therefore, side, side, side congruence theorem tells me that triangle ABC is congruent to triangle CDA, side, side, side congruence theorem. So by CPCTC, angle 1 is congruent to angle 3, angle 1 and 3, and 2 and 4. By CPCTC. Therefore, by the converse of the alternate interior angle theorem, you're going to have AB parallel to CD. Okay, so because of 1 and 3 being congruent, AB is parallel to CD. And because 2 and 4 are congruent, BC is going to be parallel to DA. And this is by the converse of the alternate interior angle theorem. And hence now your proof is finished. So what did I do? I proved that it's a parallelogram. Well, wasn't it like that before? No. The only thing we knew is that the opposite sides were congruent. So now I just showed you that it's a parallelogram. So now we can use it in actual applications. Let's take a look at the next theorem. Okay, in the next theorem, you are given that those angles are congruent. So let me see where I have a little bit of space here. Right here. All right, so given. Okay, we are given that angle A is congruent to angle C, and that angle B is congruent to angle D. And what do I need to prove? Well, basically the same thing that I just proved a little bit ago. That AB is parallel to CD, and that BC is parallel to AD. I need to prove that. So this one's going to be more like mathematical, not so much with diagonals. So we just got to understand one thing here. Okay, I need to show that these lines are going to be parallel. So the only thing that I can use here is a consecutive interior angle theorem. So let's look at one thing here. All right, first let's start with what am I given? Angle A is congruent to angle C, and angle B is congruent to angle D. That's given. So, based on this, we know that these angles are going to be congruent, right? I mean, would you agree that the measure of angle A equals the measure of angle C, and the measure of angle B equals the measure of angle D? Okay, very simple. Definition of congruent angles. So we did learn, however, that all this is a quadrilateral. The sum is 360. So check this out. The measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D, running out of space here, is all equal to 360. The reason why is because of the corollary to the polygon interior angle sum theorem. Is the one that says that the sum of the angles in a quadrilateral is 360. Okay, so check this out. I'm going to replace these two right there with A and B. I can do that by a simple substitution. So the measure of angle A plus, I'm writing a little small here, plus the measure of angle B plus, again, the measure of angle A plus the measure of angle B, they all equal 360. And what did I do? I did a double substitution. All right. So then after this, I'm just going to combine the like terms. Okay, I'm going to combine the like terms. Hopefully I have enough space. And I'm going to have two, and it's going to be combining like terms and doing factoring at the same time. So it's 2 times the measure of angle A plus the measure of angle B. How the heck did I get that? Okay, look, you have 2 of each. So just factor out the 2. Okay, so it pretty much is simplifying. So you divide both sides by 2, and you get the measure of angle A plus the measure of angle B equals 180. Division. So just think about this. These are consecutive interior angles and they're supplementary. Okay, this will imply, okay, think about this, A and B. That implies that BC is parallel to AD. And also, if you were to replace this B with D, based on this, you would get that the 2 other sides are parallel. So we're going to save a step here and say here that AB is parallel to CD. Okay, and this is by the converse of the consecutive interior angle theorem. Whoop, can't see it. Sorry. So pause the video so you can copy the notes. All right, so let's begin our examples. Okay, so we're going to do examples number 1, 2, 3, and 4. All right, here's example number 1. Okay. It says, an amusement park ride has a moving platform attached to 4 swinging arms. The platform swings back and forth, higher and higher, until it goes over the top and around in a circular motion. In the diagram below, AD and BC represent 2 of the swinging arms, and DC is parallel to the ground L. Explain why the moving platform AB is parallel to the ground. Well, the only thing that they tell me here is that L is parallel to DC. That's provided already for me. If you look at quadrilateral ABCD, the opposite sides of the quadrilateral are congruent, which means that this is going to be a parallelogram. So because AB is congruent to DC and AD is congruent to BC, because those 2 opposite sides are congruent, then this is going to imply that ABCD is a parallelogram. Right? It's a parallelogram. Okay? And that's by the parallelogram opposite side converse. So if it is a parallelogram, by definition, AB has to be parallel to DC. Okay, by definition of a parallelogram. Now think about this. If L is parallel to DC and DC is parallel to AB, by transitive property of parallel lines, L is going to be parallel to AB. Okay, that's called the transitive property of parallel lines. We covered that, can't remember when, but we've covered that before. That's example number 1. Let's look at the next example. Okay, so the way to solve this is exactly the same as the last lesson. So for what values of x and y would these be a parallelogram? So if we have to assume that it's a parallelogram, so therefore you would have to have 2x minus 1 equal to x plus 9. And also, okay, y equals x plus 7, which I can't solve yet until I solve for y. So these 2 are congruent, these 2 also. So you minus x, that gives you x minus 1 equals 9. Add 1, x equals 10. And then you use that answer to plug it right in there. Then y is going to be equal to 10 plus 7, which is 17. So you have to assume that it's a parallelogram so you can equal the opposite sides, because you have to assume that they're congruent. So you set them equal to each other, you solve for x, and then go back and plug it in onto the other one. So that, ladies and gentlemen, is example number 2. Now let's look at example number 3. Now, why on earth would someone build a door that looks like this? I have no idea. But hey, I don't know. Somebody just drew something like that. So the doorway shown is part of a building in England. Oh yeah, but blame it on the British. Over time, the building has leaned, which you figure the door would break, right? Explain how you know that SV is congruent to TU. So here's the thing, okay? The opposite sides parallel and congruent theorem states that if you have a quadrilateral that has a pair of sides that are both congruent and parallel, then this is going to be a parallelogram. So here, because you do have ST parallel to VU and ST congruent to VU, that is going to imply that STUV is a parallelogram. Parallelogram by it's called the opposite sides parallel and parallel, that's supposed to be an and congruence theorem, okay, which is at the bottom of page 207, by the way. Okay, so that's a parallelogram. So because it is a parallelogram, okay, now we can imply that SV is going to be congruent to TU, because we know that the opposite sides of a parallelogram are congruent. So opposite sides of a parallelogram are congruent. Therefore, you may not know that, but that's a symbol for therefore. Use that a lot in college, by the way. Therefore, SV is going to equal TU. It means that their measurements are going to be the same. And that, ladies and gentlemen, is example number 3. Let's look at example number 4. And the last example for this video. All right, for what value of x is the quadrilateral CDE a parallelogram? So remember we talked about how the diagonals, if they bisect each other, then it's going to be a parallelogram. So here you notice that this is congruent to this. So that means that DF is a bisector of CE. So in order for CE to be a bisector of DF, these two right here have to equal. So 5x minus 8 equals 3x. Subtract 5x and you get negative 8 equals negative 2x. Divide both sides by negative 2 and x is equal to positive 4. So x equals 4. And you can go back and plug it in. That's going to be 12, and that's also going to be 20 minus 8, which is 12. Just in case it were to ask you for the segments, like the lengths of them. And that is the last question for lesson 7.3. Thank you for joining. Don't forget to subscribe.